Okay, so what kind of machine does Turing have in mind? So what's a Turing machine then? Turing machine consists of, well, first of all, a Turing machine, right, isn't something actual, right? A Turing machine is an abstract mathematical concept. But you can imagine what the Turing machine does by imagining an infinite tape. And this infinite tape has sort of a read-write head attached to it. So the read-write head can tell the tape is divided into squares, and the read-write head always is looking at one of these squares. And it can tell which of a number of a finite number of symbols is written on the square that it's looking at. And it can also change the symbol that's on the tape, right? So if you can go on YouTube and find videos of people who have actually built Turing machines like that in Lego Mindstorm, and or there's one where the tape is actually a piece of film, and the Turing machine actually writes with a felt tip pen on it. It's very neat. But that's not the Turing machine, right? The Turing machine is just the abstract model of what happens in this computation. So you got a tape. It's divided into squares. The tape is infinitely long. So the tape sort of represents the storage space that the computer has, right, or the Turing machine has. The Turing machine can tell for the square that it's currently looking at which symbol is on it. So for instance, the square might be blank. There might be no symbol on it, or it might contain a 0, or it might contain a 1. And then it can erase that and write a different symbol on it. And then it can also move the head. It can move one square to the left or one square to the right. And how it does that, right? So whether it writes something on the tape, or whether it goes left, or whether it goes right, depends on two factors in every step of the computation. The first one is what symbol it's currently reading, and the other factor is the program. All of that is, of course, determined by the program. And the program tells the machine, whenever it's reading a certain symbol, and the machine is in a certain state, then it should do one of a number of possible things. It could be write something, erase something, go left, go right, and then go into a different state. So the Turing machine is also capable of remembering a finite number of states that it can be in. And depending on what it's reading, and depending on what state it's currently in, it might go into a different state in the next step. Okay, so we'll look at some Turing machine examples in a second, so hopefully that will become clear in due time. Now, Turing machines can do a number of things. One of them is, of course, computing computable numbers. So a Turing machine, you can think of a Turing machine or the execution of a Turing machine as you have an empty tape, and the Turing machine is in state 1, and then it just starts doing what the program is telling it to, right? So for instance, it's scanning an empty square, and the program says, if you're in state 1 and you're scanning an empty square, just go one square to the right, and go into state 2. And then the Turing machine will scan another blank, but it will now be in state 2, and the Turing machine program will tell it to do something else. If it's in state 2 and it's reading a blank, for instance, it might tell it to write a 1, right? So a Turing machine will in general, do all kinds of things, and certain Turing machines will just keep on writing zeros and ones, infinitely many, right? And if you have a Turing machine that does that, then that sequence of zeros and ones that the Turing machine is writing onto the tape, that's the number that the Turing machine computes. Okay? Of course, there's also a second kind of task that Turing machines can accomplish, and that's probably the more familiar one. Namely, they can compute functions, or they can sort of transform inputs that an operator is writing onto the tape before the machine gets started into an output, which is what's left on the machine after the Turing machine finishes or halts. Turing machine halts if it finds itself in a situation where the program doesn't tell it to do anything anymore, right? So it's scanning a certain symbol and it's in a certain state, but there's no program instruction that says, when you're scanning that symbol and you're in that state, do something, right? then it halts. So the function that the Turing machine computes in that case is the mapping from the possible inputs that the operator can put on the machine, on the tape before the machine gets started, to whatever output is left at the end of the execution of the machine. And here we might, for instance, think of inputs as natural numbers coded by a sequence of symbols of 1 on the Turing machine tape. Okay? So, for instance, if you write 5 ones on the Turing machine tape, and then you start your Turing machine, and at the end you have 10 ones on the Turing machine tape, right? That might be a Turing machine that computes the function 2 times x. Right? It always doubles the number of ones. Right? Turing machines might also, in certain cases, certain Turing machines might also always just give you a result of 0 or 1. And those are Turing machines that test for a certain property, right? So, for instance, a Turing machine which, when started on an input tape containing n ones, right? It does its thing, and at the end, there's a 1 on the tape if and only if the n was even, and otherwise there's a 0 on the tape, right? So that's a Turing machine that decides the question of whether the input is even. So here are some examples, 2 examples of Turing machines. One Turing machine that computes a computable number, namely 1/3. It's got 2 states, state 1 and 2, and 2 instructions. One instruction, the one below, right, says if you're in state 1 and you're reading a blank, the hash sign stands for a blank, then you should replace whatever you're reading right now on the tape by 0, and move 1 square to the right, and then go into state 2. And if you're in state 2 and you're reading a blank, then write a 1 and also go 1 step to the right. Right? That's the arrow going from state 2 to state 1, the top arrow. Right? So that's a very simple program. And what that program does, when you start the machine in state 1 on an empty tape, it just keeps writing 0, 1, 0, 1, 0, 1, 0, 1. And if you remember, that's exactly the binary expansion of 1/3. Right? So that's a program that computes the computable number 1/3. And really, the Turing machine is given just by those 2 instructions, the 2 instructions that I've written down in the angle brackets at the bottom. Now here's a Turing machine that tests whether a number n is even. Right? So it's a Turing machine which is intended to be started on a tape which contains a sequence of 1s. Right? And the number of 1s on the tape, that's the input. Right? So if you, for instance, you write 5 1s on the tape, then you put the Turing machine on the leftmost square of that sequence of 1s and put it into state 1 and start running it. Eventually, it will halt. Right? And in that case, if you started on 5 1s, it will halt and have written a single 0 on the tape, and that's the only thing left on the tape. Right? So in that case, the Turing machine will have said 5 is not even. Right? If you do the same thing with 8 1s on the tape, it will take a little bit longer, but in the end, it will have written a 1 on the tape, and that's the only thing that's left on the tape. Okay? So I'll leave you to contemplate what that Turing machine does at home. But we can look at what it does without contemplating it much.